Hello and welcome back. In the last several videos we have learned a lot about forces and about Newton's laws of motion that relate to those forces. Now it's time to apply Newton's laws of motion to solving real-life problems. We're going to start with a static equilibrium example that deals with a chandelier that's hung by two ropes. So here's the problem we're looking to solve today. It says a 150 kilogram chandelier is hung from the ceiling by two ropes. The ropes form an angle of 60 degrees above the horizontal, and it's asking us for what the tension in each rope is. So the key pieces of information are the mass of the chandelier and the angle of the ropes. By the way, how do we know that this 150 kilograms is mass of the object and not its weight? Well, we know that based on the unit. Kilogram is a unit of mass, and it's a measure of how much matter the object has. Weight, on the other hand, is the force of gravity on a given mass, and weight is measured in units of force since it's a force. So the units of weight would be things like pounds or Newton. For the next couple of weeks, as we will be working with applications of Newton's laws of motion to solve example problems, we're going to be following these solution steps over here. So first we will draw a picture capturing the situation. Next we will draw a free body diagram of the object of interest using the steps we discussed in the previous videos. Once we do that, we'll define our coordinate axes and then look at all the forces acting on the object, and the forces that are acting along x or y axis we're good with, but the forces that are not acting along one of these axes, we got to split it into the components along these two axes. And once we do that, finally we apply this Newton's second law, which says the sum of all the forces equals mass times acceleration in the x direction and in the y direction. So let's get started with that. Here's a picture of the situation. Here's the ceiling. Here's the chandelier that's just shown as this little dot. And here are my ropes. Rope 1, rope 2. These ropes, it says, are at an angle of 60 degrees above the horizontal. So this angle is given to us. And the mass of this chandelier is also given to us. Mass is 150 kilograms. And it's asking for the tension in the ropes. So next step, to draw our free body diagram, here's our particle representation of the chandelier. I'm not going to draw the circle and go around it, but it's good for you to do that consistently until you get comfortable with this. But as I go around this, the only contact forces are tension from this rope and tension from that rope. So let's show those two forces. I got T1 over here, T2 over here, and both of these are at 60-degree angle with respect to the horizontal. Remember, tension is a pulling force that acts along the rope. There are no other contact forces, and since this is near the surface of the earth, we have the weight as a long-range force to consider. So here's the weight of the chandelier. Okay, we got the free body diagram, and now it's time for us to choose the axes. In this case, the simplest axis seems to be our traditional axis of x-axis to the right, y-axis to the top. So that's what I'll go with. And now I can go around this and see that weight acts along the y-axis. So we're good with weight, nothing to do there. But T1 and T2 are neither along x nor y-axis. So we got to look at this fourth step here and split these into components that act along each axis. So here are the components of T1. So I got T1x over here, and I have T1y over here. And the same for T2. I got T2x pointing to the left and T2y also pointing to the top. So once we do that, we no longer need T1 and T2. We can just consider their components. So I'm going to draw a cleaner version of the free body diagram here with just the components of the forces. I got T1y pointing straight up, T2y pointing straight up, W pointing straight down, T1x pointing to the right, and T2x pointing to the left. The last step is to apply Newton's second law, which says that the sum of forces along the x-axis has to be the mass of the object times the acceleration along x-axis and the same is true for the y-axis. So let's see what happens when I apply that to this particular situation. So on my x-axis, I've got only two forces, T1x and T2x. So to add them, I take T1x, I put a plus in front of it to remind myself that it's a positive value, and then to that I add minus T2x because T2x is a negative number. So when I solve for the actual variables, I'll only get the positive magnitudes. The direction is taken into account when I set up these equations. So the sum of forces in the x direction has to be the mass times acceleration in the x direction. What is this object doing? The chandelier is hopefully just sitting there being supported by the cable and not accelerating anywhere. So the x acceleration will be 0. So this whole term simply goes to 0. So the sum of forces will be 0. In fact, the word static equilibrium tells us two things. The fact that it's an equilibrium tells us that there is no acceleration. Equilibrium simply means acceleration is 0. Static, on top of that, tells us that the velocity is also 0. The object is at rest. So this simplifies to T1x minus T2x equals 0. And since I'm interested in finding the tension and not the components, let's write these components in terms of the tension and the angle that was given to us. So here's T1, here's T1x, here's T1y, and here's T, and this angle is known to be 60 degrees. So writing T1x in terms of T and the angle, I get T1 times cosine of 60 degrees. The reason it's cosine is because T1x is adjacent to this angle, minus, I can do the same thing for T2x. I'm not going to draw the picture, but you can do that for your practice, and that'll give you T2 times cosine of 60 degrees equal to 0. And moving the T2x over to the other side, I will get T1 cosine 60 equals T2 cosine 60. Now this cosine of 60 is a number, and if I divide by that number, I can cancel this from both the sides. So solving the equilibrium condition along the x-axis gave me the result that the tension in the two ropes are equal, which makes sense. I've got a symmetric situation here with both ropes having the same angle, so it makes sense that they share the load of the weight of the chandelier equally. Now let's see what happens along y-axis. I've got T1y, which is a positive, plus T2y, which is a positive, plus weight, which is a negative. So that's the sum of all the forces along the y-axis, equals the mass times acceleration along y-axis, and that acceleration is also 0. This object is not accelerating in the y direction either. And from this triangle, sorry, this here was T1, and from this triangle, because T1y is the opposite to this angle, I will get T1y as T1 times sine of 60 degrees, plus same thing for T2, it'll be T2 times sine of 60 degrees equals W. I've added W to both sides to move it over to the other side. And because T1 and T2 are both equal, I can write this as T1 sine 60 degrees plus T1 sine 60 degrees, where I've substituted T1 for T2, equals the weight, and the weight is nothing but mass times acceleration due to gravity. So this gives me 2 times T1 times sine 60 degrees equals, now I know the mass of this, 150 kilograms, times the acceleration due to gravity, 9.8 meters per second squared. And so solving this with your calculator, you will get T1 equals 849 Newton. And going back to this equation over here, since T2 equals T1, I also have T2 is 849 newtons. Both of the ropes carry the burden of the chandelier's weight equally. And that's it. So this is how we solve a static equilibrium problem. But you will see as we move on to dynamic equilibrium and dynamics problem, the process that we follow will always be the same. This slice of physics introduced you to the standard method of solving static and dynamic problems. and took a simple example of a chandelier hung in equilibrium by two ropes.